All right, 6.2 B, double angle identities. So today we're going to introduce these double angle identities, and then we're going to use those identities to simplify just basic trig expressions. First of all, we're going to prove the double angle identity that sine of 2 alpha is equivalent to 2 sine of alpha cos of alpha. So how can we do that? We're going to use a sum and difference identity to do that. So technically, when I think of 2 of something, technically I could rewrite this as angle alpha plus angle alpha. And so if I add those two together, I'm going to get 2 sine of alpha. So this comes from our sum and difference identity, where really this second angle alpha is going to relate to our angle beta. And our sum and difference identity for sine of alpha plus beta is sine of alpha cos of beta plus times sine of beta. But in relationship to this identity, beta really represents the same angle as alpha, so I'm going to replace my betas with another angle alpha. So what I end up with is I can collect these two expressions, because these expressions are technically the same, doesn't matter the order in which we multiply two values. So sine alpha cos alpha. So using our sum and difference identities, we've just proven that the double identity for sine of 2 alpha is equivalent to 2 sine of alpha cos alpha. And then these are also the rest of our double angle identities. We're not going to prove it. We're just going to kind of trust that they are true. So sine of 2 alpha is 2 sine alpha cos alpha. There are 3 different ones for cos of 2 alpha. And so you would use these in relationship to whether you want to be working in cos and sine, just cos or sine. Okay, so cos of theta minus sine of theta, or sorry, alpha, 2 cos squared alpha minus 1, or 1 minus 2 sine squared alpha. And then our tangent identity is 2 tangent alpha over 1 minus tan squared alpha. Okay, so it says express the following in terms of a single trigonomic function. So when I think about rewriting this as a single trig function, this to me looks like my double angle identity for sine of 2 alpha. And in this case, my alpha would represent 4x. So how would I write this as a trigonomic identity? Well, using my double angle identity of sine of alpha, 2 sine alpha cos alpha, I could rewrite this to be sine of 2 times whatever alpha is. In this case would be 4x. So this would be sine of 2 times alpha, just 4x. So we'd be left with just sine of 8x. Okay, so there is our single trigonomic. All right, similarly, try to focus this better. Okay, cos squared of 1/2 alpha minus sine squared of 1/2 alpha. Again, I'm going to go to my identities, and this looks very similar to this expression. Cos squared alpha minus sine squared alpha. But in this case, we're talking, the angle is represented by 1/2 of alpha, but that's okay. So from our identity, technically alpha is representing 1/2 alpha. So in my identities, this would be equivalent to cos of 2 alpha. So this would be cos of 2 alpha, but alpha in this case would represent 1/2 of alpha. So this simplifies to just cos of alpha, because 2 times 1/2 would be 1. And then alpha in this case would represent pi over 6. So 2 tangent of alpha minus over 1 minus tan squared of alpha is equivalent to tan of 2 alpha. So in this case, my angle would be pi over 6 if I multiply pi over 6 by 2, I get a single trig ratio of just tangent of pi over 3. Okay, so that is starting to use and recognize our double angle identities. All right, moving on to example number 2. It says, given the expression sine of 2x over cos of 2x minus 1, first, what are the permissible values for the expression? Okay, so we want to figure out, basically talk about the domain of this function. Okay, so in order to find the permissible values of the function, we need to find the non-permissible values of the function. So when I look at this expression, we know that this entire expression cos of 2x minus 1 can equal 0. So what I'm going to do is I'm going to actually solve this expression for x to figure out my non-permissible values. So if I were to solve this, right, cos of 2x, so I'm going to isolate this cos of. At this point, remember 2x is part of the angle for cos, so I can't divide by 2 here. So I'm going to replace 2x with an alpha, and I'm going to just solve using my unit circle when cos of theta is equal to 1. Well, when cos of theta is equal to 1 would represent my 0 radians point and 2 pi radians. Theta is really equal to 2x, so now I'm going to replace theta with 2x, and now I'm going to go and solve this for x. Well, if I divide by 2, this is still 0, but my other non-permissible value is going to be pi. Okay? And then when you think about how often this is going to reach these expressions, right? These are all going to be related to within a pi radians. Because technically when I solve this for theta, I could rotate another rotation around the circle and get 4 pi. If I divide this value by 2, I get 2 pi. So non-permissible value is going to occur at every pi. So what are the permissible values? So we're talking about what x can equal. So that is really talking about the domain here. So we're going to say x is an element of the reals, except that x cannot equal every pi n, where n belongs to the integers. Okay, so those would be my permissible values versus non-permissible values. We'd just state this expression. All right, so second bullet says simplify the expression into a single trigonomic function. Okay, so when I look at this, recognize that sine of 2x is my double angle identity. I'm left with 2 sine of x cos of x. I'm also going to recognize that cos of 2x can be replaced with a number of things. So what I am trying to simplify this expression. So when I look at this minus 1, I want to somehow eliminate this negative 1. Well, to eliminate a negative 1, I'd almost have to add a 1 to it so that those values cancel. So looking at my identities, which of these expressions would have a positive value to it would be this. So I'm going to change cos of 2 alpha to a 1 minus sine squared alpha, or sine squared x. So I'm going to change cos of 2x to a 1 minus 2 sine squared x. And then I have this negative 1 still. You see what's going to happen is these negative ones are going to cancel. So now I'm left with just 2 sine of x cos of x over a negative 2 sine squared x. So from here, some things can start to cancel. So our 2's cancel. This sine of x is also going to cancel with one of these. So what I'm going to be left with is a negative cos of x in my numerator and a sine of x in my denominator. Well, as a single trigonomic function, cos over sine is equivalent to cotangent. So our single trigonomic ratio would be a negative cotangent of x. Okay, and then it says verify your answer using technology. So using technology on your calculators. Right, we'd want to make sure our calculator's in radian mode. Okay, so this is always a way to verify your identity, is to start with your original expression in y1. So if I go sine of 2x in y1 divided by cos of 2x minus 1, and then in my second, in y2, I'm going to go a negative 1 divided by tangent of x. Okay, so again, function a thicker line. I'm going to change my windows from 0 to 2 pi, because that's what it says to graph it in. Negative 5 to 5 is a fairly safe zone. So again, there's my equation, sine of 2x divided by cos of 2x minus 1, and negative tangent of x. If I graph this, I should have this non-permissible value here at pi. And then here's my second graph. So you can clearly see that this is an identity because, or the expressions are equivalent because they're graphing the exact same graph. All right, and that is all for double angle identities.